For this clip, we can discuss about cellular system, where if we want to increase the number of users supporting by the system, we have to apply the concept of frequency reuse. So as we reuse the frequencies, there are going to be interference among cells. How do we deal with this, and how do we determine that interference? So let's start with the assumption, right? So we have a cellular system where we use frequency reuse, and frequency reuse factor is n. Remember what is n? N is an integer. It also indicates the number of cells in a cluster. Those cells in the cluster are not using the same frequency channels. So each cell is allocated non-overlapping frequency channels. Or in another words, right? So every n cells, we're gonna repeat the frequencies, or we're gonna reuse the frequency. Okay. So n, where does n come from? We can determine n from this. So n is equal to I squared plus I multiplied by j plus j squared. Remember, I and j has to be integer greater or equal to 0. This formula come from the assumption that we assume the cells is hexagon. So let's look at example to get better understanding of this. Let's assume the system has limited bandwidth, and the transmission bandwidth can support only 35 frequency channels. So this is just example. In real system, the number of channels will be much bigger than this. But for the purpose of illustrating the concept, we assume that it's only support 35 frequency channels. If we don't apply any frequency reuse, so only 35 people can be supporting for this cellular system, which is very low. And we assume that we're going to apply frequency reuse with the factor 7, or 1 per 7, or 7. Where does 7 come from? This is when we set, for example, I is equal to 2 and j is equal to 1. Or you can set I equal to 1 and j equal to 2. Okay, so that means one cluster will consist of 7 cells which are not using the same set of frequencies, so they are not interfering with one another. So let's illustrate it here, right? So this is a cluster where we have 7 cells, right? 1, 2, 3, 4, 5, 6, 7. All these 7 cells are gonna use all the frequency channels. So remember, there are 35 of them, and there will be assigned non-overlapping frequencies. So that means each cell is assigned 35. That's the total number of frequency channels, and there are 7 cells. So each cell will be allocated 5 channels. That means if we zoom in, right, if we look at one cell, there's a base station in the middle, right? So this base station only have 5 channels, and it can support 5 users concurrently. Okay, and this set of frequencies will not be interfering any cell in the cluster because they are not using the same set of frequencies. Okay, now that means this 7 cell can support 35 users. Well, we can do this pattern elsewhere, and that cluster will support 35 users. And if we keep repeating this pattern all over the area, we're going to support more users, as you can see. Okay. Now, if they're in densely populated area, right, we can shrink the size of the cells. So we'll be able to support more users. Okay. Now, since this pattern is repeat elsewhere, so the frequency, the same frequency will be used elsewhere, which there will be interference if they're close enough. Okay, so we're gonna take a look at how that interference gonna come into a play. So let's take a look at this. Okay, so we have a cluster. Let's assume this is a cluster, and we only focus on one cell, right? So this cell will use some set of frequency channels. we assume that the radius of all the cell is equal to capital R. Okay, and remember this cluster pattern of this cell cluster will be repeated elsewhere. So next cluster will have the same sort of cell that use the same set of frequency. Okay, so this two cell, right, will interfere with one another because they use the same set of frequencies, but there's some distance between them. Okay, so the interference will not be strong, right? So we assume that distance between this what we call co-channel cells, right? So co-channel cells are cells that use the same frequencies. The distance is equal to d. Okay. Now it's not only this cell, but then there are other five co-channel cell that is close to the cell in the middle or the cluster in the middle. So there's this guy, there's this guy, there's this guy, this guy, and this guy. So there are in total 6 co-channel cells, which is closest to the cell in the middle, and all of them are distant d apart. Okay. Now you might ask, what about other cluster which is farther? Well, of course, there would be co-channel cells which are farther away, but those cells will not be affecting that much because of the larger distance. So we're gonna focus on this 6 cell, which are the closest to the cell that we are considering. Okay. Now we'll determine the interference. Let's assume the most vulnerable user, which is the cell 8 user. So if we zoom in, right, and we assume that there's a user which, right, sit on the cell edge, right? So there's a base station in the middle which can transmit the intended signal to this user, and let's compute that signal strength. So the receive power, right, for that cell edge user can be approximating as this, right? So we have P0, this is the power at the breakpoint distance or the reference distance, multiply with D0, right? Remember that's the reference distance divided by R. Remember, because the user that we are considering at the cell edge and the radius of the cell is equal to R. This whole thing raised to power of n. So the n, remember, this is pad lot exponent. It's between 2 and 4, depending on the environment. Okay. Now P0, right? So remember, what is this P0? So P0 is the receive power at the reference distance. Usually it's very close to the base station. So we're gonna approximate this as the transmit power from the base stations. Okay. So it's approximate of the transmit power from the base station, and all the base station will use the same power. So we're gonna approximate that the transmit power from the other base station is also equal to P0. Okay, so we got the receive power. Now let's go back and look at the interference. So remember, the interference is coming from the co-channel cell. Okay, so from these base stations, right, they use the same set of frequencies, so the signal will be interfering with this user, and we're gonna say the distance is approximately d. Okay, this cell to this base station to, right, it's gonna transmit the signal, and it might, if the power is strong enough, right, there may be a chance that it's gonna interfere with this cell edge user, and all the other 6 cells, or the other 4 cells. Okay, so if we take a look at the interference, right, from the co-channel cell, right, again, P0 is approximately the transmit power from the base station. D0, that's from the reference distance. divided by D, right? D, remember that's the distance between the interference base stations, right, to the intended to the cell edge user, and then raised to power of n. Okay. Now we're gonna measure the quality of the signal by looking at this what we call signal to interference power ratio, okay, or SIR. What is this? It's the ratio between the received power of the intended users, right, divided by all the interference power. Okay, so that's where the name comes from, signal to interference power ratio, right, or SIR. Okay, so the received power for the signal, for intended signal, is this, right? We determined that earlier from interference base station is this. Now remember there's gonna be 6 of them, so you have to multiply with this number, right? So I0, what is I0? I0 is the number of nearest co-channel cell, right? Normally it's equal to 6, right? Later on we're gonna learn how to cut this down, okay? So with this we can simplify, and we have that SIR is equal to this, right? 1 over I0 D over R raised to power of n. So if you want to increase signal to interference ratio, you want this ratio D over R to be large. That means you want distance between the current cell with its co-channel cell to be big. Okay, so D big, right? And also you want to cut down the number of co-channel, the number of nearest co-channel cells. Okay. Now, because of hexagon, the geometry of hexagon, it can be determined that D over R, this is equal to square root of 3n, right? So remember, n is frequency reuse factor. So if n is big, you see that the ratio between the distance of the co-channel cells and R is gonna get much bigger too, and that makes sense, right? If reuse factor is big, that means the cluster of cell will be big too, and the distance between the cell in the cluster, between two clusters, will be big as well. Okay, so with this we have the formula. We can determine SIR, right, or signal to interference power ratio, as this. Now normally when they express SIR or SNR, we usually do it in terms of dB. So if we convert this into dB, then we simply take 10 multiplied with log base 10 of SIR. Okay, and then we can express this in dB. Now if you look at this formula more carefully, you see that if we want to increase SIR, maybe you want to increase N, right? You want to increase frequency reuse factor. With that, D over R will be getting bigger, so the interference will get weaker, right, or smaller, and as a result, SIR will be bigger. But as we know from the past, if you increase frequency reuse factor, what happens is the number of total channels will be divided into many cells, and that means it's going to be less efficient. And you see in the past that the capacity of the system will be decreasing. So we have to balance this very well, so we can satisfy the requirement of our transmission. Okay. The other way is to reduce the number of co-channel cells, the closest co-channel cell. One way we can do this is we can apply the concept of sectoring. What is sectoring, right? We want to sector the cell into many sectors. Okay, how do we do that, right? So in the past, right, we assume that the antennas is omnidirectional. What it means is the antenna is transmitting signal in all the directions. So omni means every direction equally well, right? So um, you have a transmit antennas. It can transmit in all directions, right? 360 degree equally well, right? So that's good in a way, and that's bad in a way, because it's good that uh, user in any direction can receive the signal, but it's bad in the sense that interference will go everywhere too. Okay. Now, instead of doing that, if we do directional antenna, that is antenna that is able to send the signal in certain angle only, right? So for example, if we have 120-degree directional antenna, what that means is the antenna will be able to sort of transmit in this 120-degree angle, right? Not 360-degree angle. Okay. That means in a cell, right? If we want to capture all the users, then we have to install 3 sets of this type of antennas. Okay. So first one may be here, and then it's gonna cover only 120 degree. Okay. Next set of antennas, right? It's only cover in user in this direction, and again this is gonna be another 120 degree. And then the last one, right? So each antenna will provide different set of frequency channels. So the number of channels in a cell will further divided into 3 sets. Okay, so this is going to be even less efficient, but they're going to be weaker or less interference as well. Okay, so how does that work? How does this sectoring, right, using 120 degree directional antenna will cut down the number of closest co-channel cell? Let's look at this. Okay, we come to the same setup. So we have intended cell right here. Okay, and this is in this cluster, and there are nearby cluster. Okay, there are 6 of them. So there's 6 core channel cell, because if everyone uses if all this sit together like this, then they're gonna start transmitting. So this cell will interfere with the cell in the middle. This guy also, this guy also. So that's why we have the number of core channel cell is equal to 6, right? So this is with omnidirectional. What if we have this 120 degree directional antennas? Let's see what happens. The cell will be divided into 3 sectors. And let's assume that we'll focus on this sector, which uses certain sets of frequency channels. Okay, the same pattern will occur with all the other core channel cells. Okay. Now, if we focus on this direction, you see that for this guy, this frequencies in this sector will go like this. Okay. This guy also will transmit like this. Okay, and you see that both of this will interfere with the cell in the center. What about the other 4 cells? Well, it turns out the other 4 cells, right, when they transmit the same set of frequencies, it's not gonna interfere with the guy in the middle or the cell in the middle, right? Because it's all going in this right directions, right? So it doesn't affect this guy, the guy in the middle. So we essentially reduce the number of core channel cells from 6 to only 2. Okay, so with 100 degree directional antennas, right, with uh, 3 sectors per cell, we see that the number of closest core channel cells reduced from 6 to 2. We can do this even more with even narrower angle. So if we apply 60-degree directional antennas, that means each cell we install 6 sets of antennas, right? Or each cell will be divided into 6 sectors. In that case, the number of closest core channel cells will reduce even further. I0 is just equal to 1. Okay, so SIR will be increasing. That's the plus side. The downside is this. So if we assume that we use 120 directional antenna or 3 sector per cell, okay, the number of channel for a cell, right, has to be divided into 3 sets for 3 sector for 3 sector. For example, if the number of channels per cell is equal to 24, okay, if we use 120 directional antenna or 3 sector per cell, the number of channels per cell per sector in a cell is equal to 24 divided by 3, or is equal to 8. Okay, what does that mean? Okay, so we have a cell, there are 3 sectors. Okay, so every sector will be assigned only 8 channels, or it can only support 8 channels. Okay, now if the number of users are distributed uniformly in this cell, everything is all right. But then what happens if certain sector have more user? For example, this sector, all of a sudden people are moving in these directions, right? There are more than 8 users. It won't be able to support all the user because it only have 8 channels, right? Even though all the other sector, there's only 1 or 2 users only, and there are some channels that are free. Okay, right? So this is what I'm referring to when I say it's less efficient, right? So we use the resource, which is the channel, less efficient in this case, right? When we divide the number of channels into smaller bins. Okay, this is different from if we don't do any sectoring, right? So we have 24 channels and we can support all 24 users. Doesn't matter in which directions they are in, right? Because we use omnidirectional antenna. Okay, okay, so that's a con, right? In terms of this sectoring.